Hey everyone, welcome back, OChem 1. I love it. We are still going on our alkene addition reactions with bromine and various versions of bromine. We've got two more, really one reaction, but I want to do it a couple times. And then this will end this part of our alkene additions, and we'll have some more videos. It'll be super fun. I can't wait. So let's take a look at this one. We are starting with the same just generic alkene and bromine as the last video, except check it out. We've got one difference, just like we did with HBr. Let's change our solvent and let's see what happens. And in this case, we're going to make a whole new functional groups that we haven't seen before. This is an epoxide. Have you heard of epoxy resins or anything like that? They are coming from epoxides. It is an ether, but this is a specific ether. It is in a three-membered ring. So they actually have a little bit different reactivity than a normal ether does. And we will see those as a functional group in our OChem 2 class. Awesome. All right, let me erase this. So let's work our way through our mechanism. We already know the first step. We saw that in the last video. We're going to take our alkene and we're going to react it with bromine. And remember, they're both pretty nonpolar, but when they get close in space, we're going to have that induced dipole. That part still happens, that induced dipole interaction. So we end up getting a partial positive here on this bromine and a partial negative. And then we can use our alkene as a nucleophile. So same first step, look at that. And then we do have our same choices. Oh, that's fun. We get to swing both ways with that double bond. So we could reach out and form that bond here to bromine, leave behind that carbocation. We can swing up this way and leave this carbocation. Okay. Both of these we just bonded to bromine. Now we've seen these choices before. We saw these choices with HBr. But what's different here, even though this would definitely be the winner, right? We've got that nice secondary carbocation. We actually have this bromine that the one difference is we've got bromine first, not hydrogen. We added bromine first, and there is a crap ton of lone pair all around bromine. They both fill in that space. So even though we've got some choices there, we end up getting back to that exact same place where we have just made, let's make those pink, we have just made that bromonium ion. So this is temporary. You know, bromine doesn't like to share that lone pair. So this is quite reactive. This is our bromonium ion. So this part is the same. This is the same as our last video. Okay, what's our main difference here? Water. And why do we give a crap? So we still lost a Br minus over here. We still lost that Br minus, but this is just like the earlier example. This is like Vegas. This is a numbers game. For every one of these, we probably have a gajillion waters. That is our solvent, so we are going to have a whole lot of those. So what statistically is going to be your nucleophile that opens this ring? It's likely going to be your water. Okay, you have a whole lot more of it. So which side is water going to open? We can open here or open that ring there. Let's draw it. And I'm just going to draw both of them. We kind of have two options here. And remember, this is also an SN2 reaction. Right there, that's an SN2. And why do we care? Well, in either one of these, we're going to open that ring. What does SN2 do? It inverts your stereo center. So let's draw those two options. What happens this time if water opens that ring? Well, we're going to end up with a bromine here and a water there. Okay, we end up with some charges here. Bromine got a lone pair back. Oxygen is now sharing a lone pair it's not used to. And we also are going to have, we can have two options there, right? Can't water go in on either side? So we also can form this. Oh, I think I'm going to run out of space with my plus sign there. We can have bromine here. Get that lone pair back. Oh, that looks funny, doesn't it? And then we can have water here. Okay, awesome. Now, if you were reading an organic textbook, you would likely stop here, or you would relieve this charge. Now, we could use another water or a Br minus. Okay, again, numbers wise, what is the most for your money floating around? Probably water, that's your solvent. If I use the Br minus, I just want to show you that what are we about to make as a byproduct in this reaction. Let's do that. Let's draw both of them out like this. Okay, what are we about to make as a byproduct? HBr. So when you do this reaction, you're going to make like this, but then you also just made HBr. So you can use your water also, and you just made H3O plus Br minus, same thing as HBr and water. So we just made a combination of both of these. Now, if you look in any organic textbook, you're probably going to stop there, and they're going to give you fancy vocab and call this a bromohydrin, and they're going to give you the impression that you just could totally make this all day long and that's safe. And that's absolutely not true. Let's give this the name. This is a bromohydrin. The problem is, we've learned a little bit in this class, but we're going to get deeper with it. In Mother Nature, you can form rings. In fact, if you're doing SN2 type chemistry and you've got two molecules colliding, we have something called a collision frequency. This is back in your Gen Chem 2. You may have 1 million collisions for every one that's productive. Well, part of that is orientation. Those two compounds have to actually find each other. They have to have enough energy in their collision, and they have to be at the right angle. Their orientation has to be right. Well, if you actually have a nucleophile and an electrophile, holy crap, and they're already connected, this is an awesome reaction. You just took an SN2 or even an SN1 and you just made it better, because now you don't have to wait for two strangers to find each other in the evening. You literally are already connected. So often in nature, rings form up to 1 million times faster than two separate molecules that have to smack into each other. So sure, you can make a bromohydrin, it's just not going to stop. Didn't we learn on our last test that our available lone pair could make nice nucleophiles? We did. And we learned on our last test that our nice leaving groups make nice electrophiles. So we're going to keep going. Neither one of these has to stay there. And in fact, we're about to come back to the same place. Now this is going to be somewhere of a combination between an SN1, SN2. You know, if we're in a substrate like this first one, well, you've got a secondary carbocation that's about to form if you lose your leaving group. And then if you lose that leaving group, that lone pair gets to fill in that space. Okay, you can also have the alternative. What if you've just got this as a good, decent nucleophile and it is right next to that electrophile that you get to lose your leaving group? Well, look what happens. You just made a ring. In fact, let's color code here. We just made that epoxide like that. Okay. And both of those intermediates, those bromohydrins, just made the same thing. And then what are we about to form with that leaving group? You guessed it. We've got a Br minus. that just left. That's our leaving group. We can relieve that charge, and we just made a second equivalent of HBr. That's what happens to your bromine. And then at the end of this process, you just made an epoxide. Plus 2 equivalents of HBr. Okay. Now, why do I feel so strongly about not stopping at that bromohydrin? This is old chemistry. If you want a little bit of chemistry tidbits, and we actually were to take this compound, that is a nice alternative. Let me draw it right. Hang on. I got sidetracked by my sparkle pen. Let's put a little old chemistry history in here, and let's draw a substrate that looks like this and looks like this. And let's look at that pattern. What does sulfur have on it? It has lone pair. Oh, isn't that exactly like our alcohol? Look at your spacing. You have got a nice available pair of electrons here, and you have got a nice leaving group right here. So you can do this exact same chemistry that we just did. You, in fact, can do it twice on this compound. Oh my word, that's like a take-home question from your last test. All right, and what does anybody have a guess? Just pause and guess as to what this is. If you know your old school chemistry, what this is mustard gas. This is the original mustard gas. Of course, there are more modern iterations of this, but look at that chemistry. And what do you give off in your mustard gas? You're about to make 2 equivalents, in this case, of HCl. So you would have that mustard gas in canister, and as soon as you released it, you form those rings, that sulfur version of an epoxide, and you give off 2 equivalents of HCl vapor. And now whoever is breathing that in is burning something awful. So this is interesting chemistry history there. If you want to look that up, you can look up mustard gases. Wikipedia actually has them right on that front page like that, if you're curious. So we are going to take it all the way to the epoxide. Now, often you add just a little bit of base in that reaction. Why? Because of those 2 equivalents of HBr. Remember, HBr really can fume like a mother. It is not a user-friendly reagent. So you'll sometimes see sodium bicarbonate that is added, and what it's doing is it's helping that reaction form here and here, and it's also soaking up the HBr. So this is an older way of making an epoxide. Okay, now hold your seats. This is where it gets fun. Let's take this exact same example. Let's do it again, and let's add some stereochemistry. Oh, here it is. All right, this is going to be so much fun. We're going to be drawing for a while, so if you need to pause and grab your colored pencils and your paper, although you're already trained, so you probably already have that stuff. But get ready. Let's go big or go home. Let's draw this one. So let's start right here. Let's start with our starting material, and I'm going to try and draw kind of smaller. We'll see what happens. I think we're going to have to draw in a couple lines. So let's take that first step. Let's react that alkene with our bromine. Same first step. Okay, then remember we have choices, but both of those choices go right back to the same thing. So let's just draw our 2 choices. So we can, I'm going to go ahead and color code. We can add bromine here and leave behind that carbocation. Can add bromine there, leave behind that carbocation. Okay, but we know that we don't really have choices because that's not going to last. Bromine is going to fill in that space. So let's draw that. Okay, I'm going to keep 2 of them. Why am I going to keep 2 of them? This is just like the last example. Holy crap, you have those 2 rings fused. Okay, when you make that bromonium ion, it can't be trans. You can't form a ring of that size and actually be trans, both of these bonds have to be on the same side or it just doesn't reach. And with that ring, it's not flat here. If we were to look at these rings, they are not flat. You have one up and one down. So what we're really making from this, let's go ahead and include some stereochemistry, is that we're going to have an up and a down example of that bromonium ion. All right, why do we care? You already know from the last video. Why do we care? Because this next step is like an SN2. We're going to invert. So let's go big or go home. Let's draw that whole thing out. So hang on a second. We're going to have water this time come in. Well, how many options do we have? Sweet Jesus, don't we have 4 options again? Okay, don't we have the option of adding water here, 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 and here? And with the additions of those water, if we treat that like an SN2, well, what's going to happen to our stereochemistry? So let's take all 4 of those and let's draw them out. So I'm going to add water in to each one of those. Let's start with that first one. Let's take water and let's go right here. Remember, that's a 2-step process. Those electrons go back to bromine. Let's invert that process. So we keep this part stays the same with our bromine, but now our water came in from the top. So just like the last reaction, we're going to end up, oh, we went sparkle pen on that without meaning to. Okay, we're going to end up with bromine right here, and our water just added in there. Okay, awesome. Look at that. That is trans. Just like our last video with bromine in DCM. Look, trans. You just have a water adding into that and not just a bromine. All right, so we've got 4 options. That was the first one. Let's turn right around and do it again. Let's put water in here on this bottom one. And let's draw that one out. Let's see how pretty that looks. Hey, I think I'm going to change it up and I'm going to draw them this way. Okay. All right, so if water comes in that way, the stereo center we're going to invert is that bottom one, right? So let's do this. Bromine. We got electrons back from here, okay? And then we've got water adding in on the top there. Plus charge, okay? Awesome. All right, let's do the next one. We could have water here, top, open that ring. So what's the stereochemistry on that one then? All right, well that is then coming in from the bottom. Okay, let's put our water in there. And then we opened and left this one the same. All right, and then we have the last one. We're going to take water here and open that way. So let's draw that one. Let me erase my plus so I have enough space there. All right, so that one leaves this top stereo center the same. Okay, and then we just added in from the bottom this one. So that's our BR, our water, and these electrons. Okay, awesome. So we just made 4. Now for funsies, holy crap, how many stereo centers did we just make? 2. So we also just had 4 possible stereoisomers that we just made, we could have some fun looking at, how many, or did we have 2 stereocenters, or did we have 4 possible stereocenters? So how many possible compounds did we just make there? Oh my gosh, that would be an awesome test question, wouldn't it? All right, let's take any kind of base. Again, it could be your water. It could be the Br minus. If you added sodium bicarbonate, it would be that. But let's give lone pair back to each one of those waters. And then let's see what we've got. So let's turn right around and draw it all again. All right, let's try and conserve space on this side. So what are we looking at now? We've got dashed. I'm going to just go ahead and set this up like a system. Let's draw all 4 of them. Let's do this. Let's do this. And let's do this. Okay. And then we've got a nice here, 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 and here. Okay, I love it. All right, let's put our pink back in there. We've got that, we've got that, we've got that, and we've got that. All right, let's fill in. What do we have here? We've got an alcohol. We've got our bromohydrons here. We've got the other bromohydron here. We've got this one. And we've got this one. Okay. Awesome. Are we done? No. It's about to get real. Let's do this again. Again, you have a nucleophile right smack next to an electrophile. Okay, I just don't think it's responsible to just stop here. Let's talk neighboring group participation. Let's talk ring formation. When you have a nucleophile connected to an electrophile and your spacing makes a 3-membered ring, a 5-membered ring, or a 6-membered ring, you're going to make those rings. It's going to happen. Sometimes epoxides are a little bit slower to form and the 5- and 6-membered rings are much faster, but those rings are possible. So let's take each one of them. I feel another color coming on. And let's make that ring. Now remember, this is a combination SN1, SN2. We could probably think of it as somewhere in between there, but let's take each one of those nucleophiles and lose that leaving group. And then let's see what we made, and then let's talk stereochemistry. All right, so for each one of these, remember that ring formation can't happen trans. Those bonds have to be on the same side. They physically can't reach. So whatever side your oxygen is on, it is going to stay on that side. It is literally just moving over. Just moved over. You can't go up and over and reach. So that's that epoxide. Okay, so then what is this one going to look like? Well, now we are bold here. We're going to be bold here. Oh, wait a second. So then what happens to our methyl group? Aha. We just made that epoxide. And then let's take a look at this one. All right, now your OH is down here, so the bond it's going to form has to be down there on the bottom. They have to be on the same side. Oh, that's kind of ugly. All right, then let's draw this one. Again, we're on the bottom for that oxygen, so we have to form on that bottom face here. So what's that going to do to that methyl? You're going to have to push it out of the way. That is going to invert. So now this is this epoxide. All right, so in total, how many epoxides did we end up making? Did we make 4 or did we make 2? I see these as the same and these as the same. So we have two epoxides, but they are both cis. Again, you can't form a ring trans with that three-membered ring. It's just not going to happen. There's not enough space. So at the end of that entirely intense process, we ended up making a racemic version of that epoxide. Isn't that fun? So many questions in there. I hope you enjoyed this one. Now you should have some homework that you can practice these, and then we're going to turn around. We haven't seen the last of these. We're going to turn around and use them in some problems and use them in some synthesis. So stop here with these videos and go try some of that homework, and then we'll pick up with some of these in our synthesis. Awesome. I can't wait to see you guys in person someday.